Hello, welcome back to Math 152. Today we are going to look at section 7.2, which is trigonometric integrals. So before we look at all the complicated example, let us recall the basic facts that you need to know, which is integral of sine x dx is obviously negative cosine of x plus c. Integral of cosine of x dx is sine x plus c. And either you use the u substitutions or you use just the concept of antiderivative, you should be able to see that the integral of sine nx is equals to this, and integral of cosine nx is equal to this as long as your n is not equal to 0. Now, the trigonometric identity that you need to know by heart is the Pythagorean identity, which is sine square x plus cosine square x equal to 1. You remember it come in pairs. They have another two equations related to this, which is this guy and this guy here. You don't kind of really have to remember it. You just need to derive it. So you know that sine square plus cosine square equal to 1. If you divide sine square across, then you will have this. And if you decided to divide cosine square across, then you will have this. Okay, as I said in class, this is a shorthand notation. You might not really want to use it in the exam, but you can use it to write down these two equations, and then in the exam you should just show these two equations. You should write everything in full. No shorthand notations, because I don't really know what your shorthand notations means. So make sure that you write down everything. So beside this Pythagorean identity, which we're going to use like a lot, another thing that you need to know is that we have these additions formulas for sine and cosine, the addition of the angle. So for example, sine of a plus b is given by this, and cosine of a plus b is given by this. So the way you remember it is for sine, you have sine, cosine, cosine, sine, and then a, b. And then if this is plus, this will be plus. If this is minus, this will be minus. For cosine, what you have is the cosine, cosine, sine, sine, and then a, b. But then for cosine, it's a little bit weird, because when you are adding a formula, adding the angle right here, you will do subtraction right here. And then if you are subtracting in the angle, then you will do addition right here. So the sign flipped. So if you set a equal to x and b equal to x, from these equations right here, you can easily see that sine 2x is equal to 2 sine x cosine x. And that is nothing else you can do. That's the only formula you can get from sine 2x. But then for cosine 2x, you have more choices, because if you put a equal to x and b equal to x, you have cosine 2x. And then from these equations, you can see that we have cosine square x and then sine square x, and with a minus sign right here. That's the first formula. And because we have the Pythagorean identity, we can write sine square. We can get rid of cosine square by writing cosine square as 1 minus sine square, and then you will have these equations. And if you decided to get rid of sine square, then you can write sine square as 1 minus cosine square and substitute into this equations, you will have this relationship. So you have three different ways of writing cosine 2x. Which formula you're going to use will depends on the context of the problem, so it depends. So let's get to see some example. Right, so the first example is the basic formulas. What is the integral of cosine of x dx? So right, the answer is this. It's obvious. Now, if you raise the power to 2, then things are going to be a little bit more complicated. So for cosine 2x, the key thing is that we don't really know how to do cosine square. Sorry, for not cosine 2x, but cosine square x. We don't really know what cosine square x, the integral of this term is. And the way we solve this kind of problem is try to reduce it to something that we already know. So we know, what do we know? We know how to integrate sine x, which is actually sine of any type of angle, and also cosine of any type of angle. So because of that, we know that the cosine 2x, the double angle formula here, can give you this equation, which is 2 cosine square x minus 1. So we can write this, isolate this term, move everything to the other side. So we can write cosine square x as this over 2. So as you can see right here, cosine square x is going to be cosine 2x plus 1 over 2. Now, the reason why we want to use the relationship is because now if we put everything here, so I'm not integrating anything yet, I'm just writing it down, the equivalent formulas. So once we put it down here, this integral reduces to some type of integral which is manageable for us because we know how to integrate this guy. So using the linear property for integral, we can integrate this and then integrate this. And then to find the integral of this, we know the answer is just 1 over 2 sine 2x, and then this is plus x. So you manage to get this as your final answers. So it's actually still pretty straightforward if you remember this relationship. So if you remember that cosine 2x can be written as this, and then you can isolate and cosine square x, write as this, put it inside here, and everything works out pretty well. Now let's make the question slightly more complicated. What happens if you raise the power to 3? So we know how to do power 1, we know how to do power 2, how about 3? Now the trick for this is that we will try to make this guy even because we kind of know how to do the even power. So you'll be like, we have a lot of cosine x, we can take one of it, okay, put it out, okay, pull it out, take one of the cosine x, so you have cosine square x left here. And then cosine square x can be written as 1 minus sine square x from the Pythagorean identity because we have this basic formula. So cosine square x is 1 minus sine square x. The reason why we want to do this is that because we can do u substitution now. Because if you let, say, for example, u equals to sine x, then we know that du is cosine of x dx, and we do have that cosine of x dx. So which means that if you do u substitutions, we can definitely be able to reduce all this thing to something that we know how to solve. So you can kind of like do u substitution here, like right here, and immediately writing this as your integral of 1 minus u squared du. You can do it like this. And so let me write this thing down again. So this is the u substitutions that you use. And so you can write it like here and immediately you can solve it from here. Or you can kind of like distribute this thing in and then you know how to integrate this. That's not a problem. And integrating this, you see that we are still using the same u substitutions, and then you will have like integral of u squared du, which is going to give you 1 over 3 u to the power of 3 plus c. That's the reason why you have this term right here. So the answer for this, so the answers for the integral for cosine, the integral for the cosine power 3x, the answers is right here. So the trick is that we want to do some kind of like u substitutions. So since this thing only involves sine and cosine, so if you can take out a cosine here, then you should try to write all this thing in terms of sine, because if you can do that, then the u substitutions will work. Okay, so that is what happens to the cosine power 3. Let's raise this problems to the integral of cosine to the power of 4. So for power of 4, you can't really use these techniques that you see from before, because if you try, then you realize that that's a problem. You can try to do u substitution if you let your u equals to cosine of x, then your du is negative sine x dx, which you don't really have. So maybe that is not a very good choice. So you can try u equals to sine of x. Then that is good news, because then you have du equals to cosine of x dx, which as you can see is right here. But then it is very difficult to make this guy to somehow related to sine x. So you can see that the methods that works for the previous example, that works wonders for the previous example, can't really works in this case. Okay, here the reason why it works, you can use the u substitutions and take u equal to sine x. This thing works because this guy here actually is related to sine x. So you can kind of like make the u substitution works and then just integrate this 1 minus u squared du's to get the answer. But the same techniques that works for the previous example will not work for this case. So what else can we try? Well, we can still try to invoke the equations, the double angle formulas, saying that cosine of 2. This is again shorthand notations. make sure you write down the your final conclusions in full. But this is my shorthand notation. Cosine of 2x is equal to cosine square minus sine square. So if I changes my sine square to 1 minus cosine square, you will see that this is this. So so if you move this thing, so if you write this as your main term, then you will see that we have this. And then if you divide by 2, you will see that that's that relationship. So power 4, cosine power 4 can be written as cosine square x and then square again. And then inside these brackets, you can substitute this whole thing right inside here. And then, so we are only replacing the things as in the bracket. So which means that we still have a square right here. Then, so once you have that, you can expand this because we know how to square something. So it's not going to be a problem. So this is this. So now we are squaring it. So first I'm going to take the 1 over 2 square out. So that's 1 over 4. And then now we are squaring it. So we square these terms and square these terms. Sorry. So we are squaring this term and square this term. And the middle term is obtained by taking 2 multiplied with this, multiplied with this. That's the reason why we have that. And so we know how to integrate this because we know how to integrate sine of any angle or cosine of any angle. And integrating this is obviously going to give you x. So the only thing that we don't know is this guy. But this problem here is the same problem that we encountered before, which is right here. So let's take care of that in a minute. So here we know how to integrate this, we know how to integrate this. So this guy here, we can rewrite this as cosine of 4x plus 1. So maybe if you haven't seen this before, I'm just saying that if you substitute the x to 2x, if you are having problem with this kind of concept, you can write this equation as if you are having cosine square of a box is equals to cosine let me get rid of this, is equals to the cosine of 2 times that box plus 1. So if you refer to the situation here, we need to apply this formulas right here. So our box here is 2x. So our box here is 2x. So you have 2x in our box. So cosine square of 2x will turns out to be 1 over 2 cosine of 2x times 2, which is 4x plus 1. So that is why we substitute right here. So once you have done it like that, you will see that there's no more square. Everything is just cosine of some angle. And therefore, this is something that's definitely manageable. And now we can integrate. So integrating 1 is x, integrating cosine 2x is this. They have a 2 right here. And then we are not integrating anything yet. We are just copy and paste this relationship right here. So we basically just copy down things that we have here. We just copy down things that we have here. And then this part here, we try to integrate to obtain 1 over 4 sine 4x. And this one will give you x. And then we are done. There's no more integral. And so cross multiply if you need to will give you the final answer that looks like this. Cool. So, well, you might ask, like, how do we know that for this case we have to do it like this? And then how do we know for this case we can take out a cosine x? Well, we are basically just trying. Doesn't mean that this is like the first thing that I know what to do. As you can see, previously we were also trying out some other stuff. It just doesn't really work. Okay, so this one, apparently, if you do it like this, everything will works out pretty good. Now, let's raise the power again, this time to power 5. Now, in fact, we're going to do all the way to power 6. Okay, let's look at power 5. Now, for power 5, you might think that because power 4, the computations for this power 4 case is like pretty involved. So therefore, power 5 might be very involved also. So actually, power 5 is easier to handle because the way we do it is to, again, take a cosine of x out. And then you have cosine to the power of 4x, right? Because all this multiplied together will give you the power of 5. And then the reason why this is like easier because I can say, hey, maybe we can try this u substitutions, because if you do u equals to sine x, the du will be cosine x dx, which is exactly what we have. The only question now is that can we turn this into sine x? Well, the answer is yes, and you don't have to use double angle formula whatsoever. You can just use the Pythagorean identity. So instead of writing 4, we have to do it like one step at a time. So we can't really do 4, but 4 is something power 4. So when you have something power 4, you can write that as something square and then square again, right? So we are doing that exactly that. So right here we're writing cosine square x and then square. And then from here, cosine square x is 1 minus sine square x, and then you still have the square. And then we are ready because we started to bring in the u now. So we have the u equal to sine x. So this is nothing but 1 minus u square and then square. So you turn all this trigonometric functions into basically just polynomial. This is polynomial. You definitely know how to square this now. So squaring this to get this, squaring this to get this, and the middle term is 2 times this, which gives you minus 2u squared. And then now it reduces the entire problems to preschool integral. And so integrating 1 give you u, integrating the u squared give you u cubed over 3, so on and so forth. And then you finally bring in the u, so that will be your final answers to the power 5. So you might start to see some kind of pattern, some kind of like a pattern, because apparently if you are having an odd power terms, apparently by splitting them like that will be you will be able to turn the question into something that is pretty easy. So maybe it will work for the cases. Let's do one more case before we move on. All right. So before you attempt, I mean, this is now power 6. So if you want, you can kind of like try this again. So you can write cosine of x dx. And then the problem is again the same thing. So if you want to have this, your u will better be sine x, because then your du will be sine x dx. But the problem is that, again, this is difficult to get cosine to the power of 5 written as like polynomial of sine x. So that is difficult because all the relationship that you have, the Pythagorean identity and all that, is designed for the square, for the even power, but not for the odd power. So you might have trouble finding relationships of relating cosine of 5x to some power of sine x, or some combinations of power of sine x. So the way to do this is actually not going to try with this. What you're going to do is, again, using the double angle formulas. So using your double angle formulas, you know that cosine square x is equal to 1 over 2 cosine 2x plus 1. So substituting this inside the cube, because you need to make a 6. So you need to make a power 6. So we can change this to 2, and then you have the 3. All these things is going to give you power 6. So now you are just going to expand this using the binomial formulas, or something that you should know is a plus b to the power of 3 is a cubed plus 3a squared b plus 3ab squared plus b cubed. Now, if you haven't seen this before, this is called the binomial formulas. These are the binomial coefficients, okay? 1, 3, 3, 1, 1, 3, 3, 1. And then you can see the power of 3 get reduces from 3 to 1 to 0, and then the power of the b gets increased from power 0 to power 1 to power 2 to power 3. So this is so-called the binomial formulas. So you will have a cubed plus 3a squared b plus 3ab squared plus b cubed. So you can just simply expand all this thing out, and this is kind of like the mess. Now, this type of problem is not difficult. It is tedious. Being tedious and being difficult is two different things. Being difficult might be you don't even know how to start. Being tedious means that, well, I know how to start. It's just I'm not going to do this. It's just so much work. That's being tedious. So, for example, why do I say this? This is being tedious because you actually know how to integrate every one of them. Because integrating this is x, integrating this is the basic formula, integrating this is, we have done it before, you know the techniques. And actually, we also know how to deal with this before. Because you remember that we actually started from power 1 and go to power 2 and then go to power 3. So we are using the power 3, we are using the power 2. We already know how to do this. It's just that kind of like we have to repeat all that process again. So yeah, let's do that. So so you might want to pause it and do it yourself. So so let's do this. So we have these terms right here, these terms right here. I'm just multiplying out the pulling out the constants and multiplying in the 1 over 8. So you have that. Now, so this integral here is what I refer to as I1 because I want to compute it separately, because otherwise this thing is just going to get very complicated. So when things get complicated, this is something that you can do. You can rename this. You can rename this integral to be I1. You can rename this integral to be I2. You can rename this integral to be I3. You can rename this integral to be I4. I mean, you don't really have to do the I4 and I3 because you kind of like can write down the answers right away anyway. But this is definitely something that you can do. Right, so let's compute the hardest part, which is I1. So again, power 3, right? So you remember that power 3, we can take one of the cosine out and write this thing as something that is related to sine square and then use this U substitutions. And also because the angle here is 2x, so do not just simply copy and paste the substitution that you have for sine x, because for sine x, your du is cosine x dx, but then for sine 2x, your du is actually 2 times cosine of 2x dx. So things is going to be a little bit different. You have to take care of all these coefficients. So be careful about that. So in order to have this du, I would need to bring in a 2. So I need to divide by 2 so that we still have the equality. All right, so we still have the equality from the equations before this. So now this is nothing but du, and in fact this thing turns out to be 1 minus u squared, and then we get this result right here. You don't really have to worry about all the constant terms. At the end we can just consolidate all the constant terms into one big constant terms, which we call enron. No, which we call constant c. Okay, right. So right here, once you have done with this, you can find I2. We found it. You can find I3 and I4, and we can put everything together. This is putting I1, I2, I3, and I4 together and do some algebra to simplify it, and that will be what you should get. Now, this is obviously too long to be an exam questions, but you can kind of see that actually, yeah, things are just getting tedious, but now you kind of spotted techniques, like a strategy. You can say that if you look at the integral of cosine of an even power, somehow like doing this will help. And you are integrating cosine of an odd power, somehow taking this thing out will help. And in fact, this is a summary of what we have just done. And this is the power 3, so taking out, so it's even power, sorry, odd power. 3 is odd numbers. And then somehow taking this thing out and do all this thing will work. Power 4, even power, so we have to do the substitutions. And power 5, taking this thing out, things will work very well. Power 6, yeah, you cannot really take cosine out, but you have to do this and bring this thing again, and things will work out. So in fact, this is kind of like the things that you can remember. So you might not remember exactly what's going on, because at the end, there's just going to be so many things, and there's just no way for you to remember every single thing. So at least kind of like have the impressions that for this kind of cosine to the power of something, or even sine to the power of something, somehow if this even, you try this, somehow it's odd, you try that, but you might not sure which one to try. And it doesn't take you a long time to realize the techniques that doesn't work. So for example, this one, if you try cosine 3x, cosine x, and then you'll be like, I don't think I can make this relates to sine at all, then you know that, yeah, that's not the thing. The other thing you can try is using the double angle formulas. So cosine of 2x equals to cosine squared minus sine squared. So I can write this as this using the Pythagorean identity, and I have this 2 squared minus 1 c2. By the way, I don't really remember all this formula. This is actually how I derived the stuff. So because I don't want to make a mistake by, instead of +1, I do -1. So I always very carefully deriving all this thing again using my shorthand. So it'll be like c2 plus 1. So c squared is equal to 1 over 2 cosine 2 plus 1. And then that is when you write down the proper thing, which is like this, is 1 over 2 cosine of 2x plus 1. And then that is like the things that you try. So you just have to have an impression of like how this thing works. So it's like either you take one of the cosine out, or either you use the double angle formula. Which one is it? Is it even when you do that? Is it odd when you do that? If you don't remember, just give it a try, and you should be able to see which one will give you a headache and which one will work, and you go from there, right? So there's not going to be a lot of problems. Just try to remember right now, things are getting more and more complicated. There are more and more techniques. You just have to kind of have an impression on how to deal with this kind of stuff, because in the future, few years from now, well, after you graduate on the workforce, you're doing something, you're an engineer or whatever, and then you are somehow need to integrate this. That's just no way you remember everything. You'll be like, I think we can take something out, or maybe some other stuff. Let me try. But at least I remember I can like kind of like write power 5 as something as power 4 with power 1, and then you'll be all right. Okay, all right, cool. So in fact, just want to point out that all the observations that we saw above works for the sine power as well. Okay, and also actually it works for the combinations of sine and cosine power like this as well. So when you come across integral that looks like this, for example, this is the example. Well, you might want to try the things that we learned from before, right? So I mean, you will be like, okay, so if we look at this integral, this guy is power 3. Can I write power 3 as like this and this? Can we split this thing to these two sine terms up and write it like that? Why do we want to write it like that? Because if you write it like that, maybe you use this u substitution, your du will be negative sine x dx. So then I just need to put a negative, then I will have that. If you do that, then you better make sure everything can be written in terms of cosine. And you'll be like, yeah, cosine is already cosine, and sine, obviously, I can write as cosine. So that is how your thought process should go. You are not just staring it blankly and not know what to do. You'll be like, okay, seems like I can pull out one term, which is here. Why the hell I need to pull out this term? What can I do with this? Well, I have sine x dx. Well, that's a du of something. So du of what? Well, du of this. If you have u as cosine of x, obviously, you will hope to write everything in terms of u, which is everything in terms of cosine. So cosine, you don't have to do anything on that. And then sine, you change it to cosine, and then you will turn this thing into a preschool integral again, right? So that's the thought process, right? So you'll be like, okay, maybe I can do this, maybe I cannot. You might not try like this, you might try something else, and then you get stuck. Then think about like, can I do this? And the answer is yes. So maybe you can also kind of like try to generalize this. Try to generalize this to, yeah, even odd power. Seems like odd power, I can always do this and things will work. So maybe next time, every time I see odd power, I'm going to try this first, right? You gain from experience, okay? Everyone have to start somewhere. So I'm showing you all this example and all this thought process so that you can try that next time, okay? If you can turn this thing into something that is like this, okay, do it. Anyone can do this. But not everyone knows how to convert this to this. Okay? Remember the girl, the little baby, she's 3 years old. She knows how to do this. And by the way, she knows also how to plus C, so don't forget your constant. So that's your answers. Now, so we are kind of done with the sine and cosine. It's getting a little bit boring now. So let's move to some other trigonometric functions, such as tangent and secant. Now, if you have like tangent and secants appear next to each other, this is actually something that we can play with. Well, remember that we have the Pythagorean identity, which is sine squared plus cosine squared equal to 1, and you can divide sine squared to get this. Actually, you get this cotangent square x equals to cosecant square x, and then if you need to arrange it, you can arrange it to actually, in fact, I don't need this. Yeah, divide the wrong thing. So I want to divide cosine squared to get tangent square x plus 1 equals to secant square x. So I can write tangent square x as secant square x minus 1, or I can write secant square x as this. So yeah, again, if you cannot remember all this, you shouldn't remember all this, because again, you can get it very easily from the original Pythagorean identity. Now, so apparently, we have all this relationship which we're going to exploit in a minute. And also, when tangent and secant are together, you can, there's just no way we can deal with it like straightforward using direct methods. So we're going to use a substitution method. So if you want to substitute, obviously you would not substitute something like sine x. Dude, there's no sine x here. I mean, they do. Yeah, right. But yeah. No, I'm not going to do the sine x. So obviously you were going to try like tangent x, and also try not to do something crazy, which is like you don't want to make your u equals to tangent 5x dx. That's just 5x. This is too big, because if you do it like this, your du will be like very problematic, like this, and then like secant square x, and now you usually do some easy substitutions. So we go for simplicity, right? Simple is always pretty. I think there's a Chinese proverb for that. I'm not sure. Okay, anyway, yeah, simple is good, right? Simple is good. So we will want to try u that looks like this. If you want to try u that looks like this, what's the du? Du will be secant square x dx. So that's a lot of secant and tangent. So maybe you can do that. Or you can use the u equals to secant x. As I said, there are a lot of this stuff hanging around here. So if you do this substitutions, your du will be secant x and then tangent x dx. That's the derivative of secant x. And again, you have tons of this stuff right here. See, these are all the tangent, secant. They are everywhere. So if you have enough to split them, for example, I can take one of the tangents out. I can take one of the secant out. And you can see now I have secant x tangent x. So that's the du of the this particular substitutions. And so let's try it. We might not know it works yet, but let's give it a try. So if we do this u substitutions, this is going to be your du. If this is your du, you'll want to keep the secant x and write everything in terms of secant x. So keep this, right? And then you just like, okay, I need to write tangent square x, actually tangent to a power of 4, okay, in terms of secant. But again, even if it is even power, we can split them into 2 like this, right? And then we can bring in the tangent x, bring in the big gun now. That's the formulas. Tangent x is secant square x minus 1. This is the secant power 6. This is the du. And again, once you see that, oh, yeah, so you reduce this integral into something that anyone know how to solve. Well, yeah, the 3 years old might not know how to expand this thing out. So maybe you will help her a little bit by expanding all this thing out, multiply this thing in. And once you get into this, she will know this is this. And once you have that, that's the answer. Okay? So I'm trying to give you the rationale behind this, which is like there's 2 different types of substitutions. And apparently by doing this, it will work. But how do you know that this particular substitution here, this thing works? You can give it a try and see what happens. It might work, and then you get another alternative solutions. It might not work, and you can try to see like exactly where the methods breaks down. So, but obviously, the u substitutions, you will either try u equal to secant x, or you will either try u equals to tangent x. So when you are doing tangent x, you have to have secant square x dx. We definitely do have that. We can get it from there, and then but you will see that if you proceed with this substitution, you will see that we will run into a problem. So you will be like, abandon this method, and then let's try this one. And when you try this one, everything works. So you get the answer right away. I just want to say one thing though. This is not something about honors or like whatever. I mean, every time if your ship is sinking, we are going to abandon ship and try another one. We are definitely not going to sink with the ship. So if you realize that there's some problems, switch approach, right? Because your approach might not work, and you will have to find a new method. So, but if you look at this particular example, you don't really know. You actually would not know which u substitution will work. This is like one of the candidate. This is also one of the candidates. And you might ask me like, so how do you know which one to use? Well, I know because I have tried before. The first time I see this years ago, I might not know which one to start, right? So you just have to give it a try and build experience. That is the reason why you need a lot of practice. So that's the reason why we give you a lot of example here, and also a lot of practice problem, so that you know what to deal with this. Okay, so we are looking at the new problem now, new example. Let's compare the previous example with this. What is the main difference? The main difference is that now we have both even power. Previously, we have both odd power. So you might also want to build your strategy from there, which is like, if it is even power, maybe I try this, it will work. Maybe if it's odd power, maybe I try this, so on and so forth, right? So now we have the even power. So again, if you want to try, you have two options for this. Obviously, you are either going for this, okay, which is your du is secant theta tangent theta d theta. You do also have a lot of secant theta and tangent theta right lying around where you can group them together and get you a du. Again, you might not know which one is the right one to try, so you have to give it a shot. So right here, if you try this, you will see it will work. Here we are using u equal to tangent theta, so the du will be secant squared theta, and we do have that. We actually have plenty of it. We have power 4, so we can spare 2 of them right here, and that will be your du. So if you decide to make this as your du, then everything else have to be in tangent theta, because you make this as tangent theta, so secant squared theta has to go. It has to go away and change to something else, and that is where you use this all the identity that you know from before. So you can write secant squared theta as 1 plus tangent squared theta, and then now you can reduce this everything into this, and if you multiply this thing out, again you'll run into a very simple integral which anyone know how to solve. So that will be the 1 over 3 power 3 u power 3 and 1 over 5 u power 5, and you will get this. Now, as I said, you should try the other substitution and see whether it works. And if it doesn't work, try to see why it doesn't work. And so you will recognize the failure and try not to repeat it next time. Okay, so let's look at another example, which is example 10. And now you might also want to compare what is the difference between example 10 and example 9 and example 8. As I said, example 8, apparently we are dealing with 2 even power, 2 odd power. Example 9, we're dealing with 2 even power. And example 10, we are dealing with 1 even power and 1 odd power. This is the odd power, this is the even power. Again, you have 2 different substitutions you can try. You can try this, or you can try this. Okay, where your du is secant theta, secant x tangent x dx, and we do have a lot of these terms lying around. You might want to give this a shot and see what happens. But if you give this substitution a shot, you will see that obviously I need the secant square, so you break this thing out from here, okay, from here. So you get that, and again, same very obvious strategy. If you using your u as tangent theta, this will be u cubed, and you have to find ways to write this as tangent theta and tangent x, and using this relationship again, we are able to do that, and you manage to turn everything very nicely into integral of polynomial in u. And again, expanding it out and reduces it to this integral, you will be able to get the answers like this, something that is like everybody knows how to do this. So you will get this as your answers. But the key thing is which substitutions, which is the one that you need to use. Because if you use the wrong thing, you will not be able to get to something that's that nice. But if you use the right thing, everything will work. It's kind of like a relationship. As I said many times, if you meet someone that is the one, then everything will work. You will get all the ways to a perfect answers. If you get to someone that is not the one, then, well, the only things that you will get is trouble. So, and remember, don't invest too much efforts when you are like having a lot of trouble. Now, this is not really true though, because sometimes, yeah, it depends. So sometimes you are struggling with that relationship. You maybe it's that method. You just have to work a little bit harder. Then you'll have a breakthrough. So, well, it will depend. So you need practice to be able to figure all this thing out. So again, do a lot of exercise. Cool. So right. So we are kind of basically seeing all this so far, all these 10 examples show us that we are actually all using the u substitutions, and if not u substitutions, we are using the double angle formulas. So this is actually what we have been doing, And we see that it works for the sine function, cosine function, combination of sine and cosine. And in fact, if you have like combinations of tangent and secant, everything also works pretty well. Same kind of methods, just use substitution, just have to figure out what to substitute. And that's basically it. So that is the things that you need to know. A majority of the problem in section 7.2 involve combination of sine x and cosine x, or tangent and secant, one way or another. And there is also another type of integral, which is this, because in Calc 1, you never learned what is the integral of tangent of x, because this seems kind of weird. Because we all know the integral of sine x dx, the integral of cosine x dx, and obviously the next thing we're going to talk about is this, but somehow your professor are not saying anything about that. So the reason why we are not saying anything about that in Calc 1 is because you don't know what is the integral of the 1 over u, like 1 over x dx. You don't know this thing yet. And in fact, for this case, we are going to use that integral to compute the integral of tangent of x. Tangent of x, as you know, I forgot the dx. So tangent of x, as you know, is the ratio of sine x and cosine of x. So again, so if you are taking this as your u, okay, if you are taking this as your u, you will need a negative sine x dx to get a du. So we do have that. We have a sine x. The only thing that's missing is negative. So we can put the negative right here and then put a negative here so that you don't change anything. So these two are really equal. So now this terms is reduces to this, and this gives you this. Now remember, integral of 1 over x dx gives you log of absolute value of x plus c. And the chain rule form will give you fx and then f prime of x dx. This will give you absolute value of f of x plus c. So so obviously using that, you have this, so you have this, so you have this. You can write your answer like this. That's fine. It's just that we can also bring the power -1 to the power, because these are log property. So we can bring the negative up here, and we have that. And this is 1 over something, so you have 1 over cosine, that will be your secant. So usually we'll write the answer as this. So what is the integral of tangent x dx? Well, it is the natural log of absolute value of secant x plus c. So that is another type of problems, which is kind of this format, is the integral of secant of x. So the integral of secant of x is also the things as a little bit weird. Now, so the way to solve this, the integral of secant of x dx, is to multiply this. So this is actually just 1, because as you can see, the top part and the bottom part, the numerator and the denominator are both same. So this is just 1. Now, there's infinitely many ways to write 1, right? So you can have like a over a, you can have like sine x over sine x, you can have like infinitely many different types. How do you know this is the 1? Well, nobody knows that until you seen it or figure this thing out yourself. So now let me just try to introduce this as an example so that you remember. Next time, if you see secant of x, if you multiply this, you will get a very good thing, because if you cross multiply this, you have secant square x and then secant x tangent x. And if you look at this and call this as your u, which is secant x and tangent x, if you take the derivative, you get secant x tangent x for the derivative of secant x, and then you get secant square x for the derivative of tangent x, and you will see that they are right here. So apparently, if you call this is your fx, the entire f prime of x dx is on top of it, which means that the integral of this is going to log of the absolute value of fx plus c, where your fx is right here, and you get the answers. As simple as that. So next time, if you see you need to integrate secant of x, well, this is the things that you need to multiply. All right, we're almost done. The last example is trigonometric functions that looks like this. Well, so how do we integrate this? There's no power whatsoever, and also the angle are all different. Well, in order to deal with this, recall that we have these addition formulas. So sine A plus B for the angle is sine, cosine, cosine, sine, A, B, if it's plus, it's plus. So if it's minus, it's minus. So when you have this, you can see that these two are the same. Actually, these two also the same, but these two have opposite sign. So if you add these two equation together, these two will cancel each other out, and you will have sine A plus B plus sine A minus B equals to 2 times of this. Okay, all right, let me say that one more time. So if you add these two equations together, these two will cancel, and then here plus this will be given here, and this plus this is 2 times of sine A cosine B, which means that sine A cosine B is 1/2 of this. So if you compare your sine A cosine B with this, then you can say that, all right, my A is 8x, and then my B is 5x. So, well, so what is this thing here on the left? Well, A plus B is obviously 13x, A minus B is 3x. So sine 8x and cosine 5x, if you try to integrate this, is the same as integrating the entire left-hand side here with A plus B is 13x, A minus B is 3x. So this whole thing here is like this. So instead of product of two sine and cosine, now you write everything in terms of summations, addition of two sine functions. And that is something that you know how to integrate. So integrating this is not a problem. You know right away that you're going to get this, and then, you know, simplify a little bit. You will have that as your answers. Okay, so this is the last example of it's not really the last example, it's the last type of questions you might need to deal with in section 7.2. Just have one last thing to point out. So same methods, nothing's different. This is the next example. So it's exactly the same methods. We have that equation, that relationship. Okay, so again, you will say A is 4x and B is 5x. You add this, you minus this, you have minus x. So according to the formulas, this thing here will be 9x and minus x. And how do you deal with minus x? Well, try to recall that we have the even function and odd functions, and sine theta is the odd function. So sine of negative theta is negative of sine theta. So you can take the negative out. And then once you take the negative out, the rest are just simple integral. And that is all the things that you're responsible for section 7.2. And that's it. On Monday, we're going to have a quick quiz on this. And then we're going to move to section 7.3. So have a good weekend, and watch this video and learn some stuff. Math is fun. So much fun. See you next week.